An optimization problem is just a take the derivative, set it equal to 0, and solve problem with an application. So your job is to set up the equation and figure out what the equation is, and then the rest of it is just calculus and algebra and stuff we've done before. So this takes all kinds of forms. So I'm just going to show you a couple of examples. So here's the first one. We have 1,200 square centimeters of cardboard to make a box with a square base and no top. We want to find the maximum possible volume the box can have. So visualize the problem first. We're either going to make a really short flat box or a tall skinny box or somewhere in the middle like a shoebox kind of looking box. You get the idea that it's probably somewhere in the middle because that's generally what boxes look like. And step one is always to draw a picture. So just, you can't really understand the problem at all until you draw a picture, and just name some stuff. All right, so that's a box. So notice it has no top, so it's just the 4 sides and the base. It's a square base, so there's no reason to give the length and the width 2 different variables, right? Because they're equal. So square base means length and width are equal, so I just call them both B for base. You can call them something else. You can call them X or whatever. So we have to decide on what B should be and what H should be, with the restriction that we have like a finite set amount of stuff to make this with. So when we say 1,200 centimeters of cardboard, mathematically, what is that? Is that the volume, the mass, whatever? No, that's the surface area. So we have a fixed surface area, and we want to maximize the volume. So the volume of a rectangular prism is just all the sides multiplied together. So it's just base times height, the area of the base times the height. So since our base is square, that's B squared times H. So that's the equation we're ultimately going to be working with. But that has 2 variables in it. And we can't take the derivative of something that has more than 1 variable in it because it's not a function. It's not a function of 1 variable B. It is a function of 2 variables. But we use our restriction. We use the fact that, okay, we only have 1,200 square centimeters of stuff. So we use that to fix this equation so that it only has 1 variable. Think about why this looks like this. This is the equation for the surface area of our box with no top. The surface area of the base is just B squared. And then the surface area of every single side is the same as BH, right? All 4 sides of the box are exactly the same. So we have 4BH for the 4 sides, and then B squared for the bottom, for the base. And then remember, we have no top. So, right, that's our simple equation for the surface area. And that's a restriction. So you'll always be given some restriction in these types of problems, because if I just said, hey, make a big box, you'd say, well, give me more material, right? We have a fixed amount of material, and we want to know the optimal box shape. So we take that restriction, and we do a little bit of algebra, and we solve that thing for H. Subtract B squared from both sides. Divide by 4B. And that's what we get. So that's our relationship between the height and the base. H is 12,000 minus B squared over 4B. We're going to stick that into the equation for volume. That way, we won't have an H in there anymore. We'll just have B's. That's what that looks like. It's B squared times H, so that's our volume. So now our volume is B squared times 1,200 minus B squared over 4B. So you see what I'm saying? That is a function of 1 variable. That's like f of x, v of b. Now b is the variable. B is the only thing that's changing. Once we figure out what b is, we can easily figure out what h would have to be. So since we're actually doing stuff with that, we're not done. We haven't done any calculus yet. Let's clean that up a little bit because we have to take the derivative. So that simplifies to 1200b minus b cubed over 4. And we can even take that one step further. Okay, just divide both of those terms by 4 and we get 300b minus 1/4 b cubed. So now we get to pick what we make b. And whatever we make b, that's going to be the volume. We want that thing to be as big as possible, right? So again, just think, is our box short and flat? Is it tall and skinny? Is it perfectly square? Is it somewhere in the middle there? We'll find out. So just think of that as f of x, and that's just, we want to find the local maximum of that function. There's some sweet spot. That's what optimization problems are. There's a sweet spot where we get that maximum possible value. So just, again, think of that like f of x. Rewrite it as f of x if it makes you feel better. 300x minus 1/4 x cubed. Taking the derivative of that is like the only easy part of this problem. That should be automatic for you at this point. So if that's v of b, like f of x, v prime of b is easy as 300 minus 3/4 b squared. So we set that equal to 0 and figure out what b is there, and that'll give us our optimal maximum possible volume. This is algebra. You should know how to do this. We're going to move the 3/4 b squared to the other side. And then probably multiply both sides by 4/3 to get b squared. That gives us b squared equals 400. Then you just square root both sides. Convince yourself that plus or minus 20 doesn't make any sense in this context. So this is the thing with story problems, whereas negative 20 would give you another min or max of this function. If you just were looking at the graph of it, it makes absolutely no sense in this context because it's the size of a box. So the only possible answer is b squared, as b is 20. In some of these problems, you could get two answers, where one would be the minimum volume of the box. In this case, it wouldn't, because if you think about, well, what's the worst box I can make? Mathematically, you would just make b 0, so you would have 0 volume. So you just screwed your whole box. So that doesn't really come up in this context. You just have to be careful sometimes. So that's it. B is 20 centimeters. We generally want to know more. The setup of the question said, find me the volume, right? So this is just like finding the y value after you find the x value of a local max of a function. Tell me what the actual volume is going to be too, the best volume. So just we're plugging b back into that equation we already made for h. We already got h in terms of b, so use that. So h is whatever 1200 minus 20 squared over 4 times 20 is, and that's 10. So the base was 20 and the height was 10. The number 1200 was arbitrary. I could have said 12 million. The dimensions of the box would still be the same, right? We found the right proportion. That number 1200 could have been anything. So in general, what we've just proven, which is pretty cool, that if you had to make a box with no top and a square base, this would be the best way to do it, no matter how big the box was, right? If it was a little ring box or a big old, Amazon furniture box, it doesn't matter. Optimally, you would make the height be half of the base. And then it's just still plugging in. I wanted to know the volume. So the volume is b squared times h, which is 20 squared times 10, which is 4,000 cubic centimeters. So with 1,200 square centimeters of surface area, the best shape we can make of this type is going to give us 4,000 cubic centimeters of volume. Here's another one. It's the same kind of thing, just almost kind of backwards. So now we have a fixed volume. We want to make a can that holds 1 liter of fluid. So just think about a soup can, a cylindrical can. And we want to know what shape our can should be, right? So we're still finding the dimensions for our container. to be able to use the least amount of material possible. So if we're making a tin can, we want to use the least amount of tin. So again, visualize what I'm saying. Is our tin going to be short and flat like a tuna can? Or is our can going to be like super long and skinny like a pixie stick? Is that still a thing? Or is it probably going to be somewhere in the middle like a soup can that you're used to seeing, right? Picture a can. They all kind of look the same way. So what these optimization problems really are telling us is like, why do they look that way? Now, this is an oversimplification of reality because you know how the material works in a box or a can or whatever. You have to fold a little bit over to make it. There are other considerations besides just dimensions, like shipping. Like, can you pack a bunch of them into a box? That's a math problem too, but it's a heck of a lot more complicated than this course. Take a graduate course in optimization sometime and you will see what I mean. It's very complicated. It's almost, some parts of it are still unsolved and unknown. Anyways, we can do this. So our volume is fixed at 1 liter. Our surface area is now the thing we're trying to optimize. We want the minimum surface area, right? We don't want the maximum surface area. We want the minimum amount of material we can use to hold 1 liter of fluid in a cylindrical shape. So it starts with some geometry. There's only 2 things that we need to give us a cylinder. We want to know what the radius is, and we want to know what the height is, right? So the bigger H is, the skinnier the top's going to be, so the smaller R is, and then we got our weird tall skinny can that you probably know isn't right. If H were very small, R would be very big, and then you'd have like a film canister looking can, which again, I think you also get the sense isn't really right either. So there's just some sweet spot, and you would have no idea what it was unless you just do what we're about to do, which is do the math. So we just have to kind of pick this apart. We need an equation for the surface area of a cylinder. So we need to make the top, we need to make the bottom. Those are exactly the same. Those are just 2 circles of metal. And then we need to make the sides. And if you think about what shape the sides actually are, they're a rectangle, right? They're a rectangle that we have wrapped around a circle to make a can. That's what all we need. There's the top, the bottom, and the sides. Now think about the length. So the height of the sides is just H. It's just the height of the can. The length of that side is the same as the circumference of the top and bottom, right? Circumference is perimeter, but for circles. So the circumference of that circle is 2 pi r. That's not calculus. That's where I got that number, 2 pi r. That's how long that rectangle needs to be to wrap around to meet the top and the bottom. So the total surface area we need is the area of that circle plus the area of that circle, which is the same, plus the area of that rectangle. Area of a circle is pi r squared, so it's pi r squared plus 2 pi r times h. The area of that rectangle is just length times height, essentially, well, width times height, so it's just h times 2 pi r. So we can just combine those first 2 terms, and that simplifies to that. So now we have the same problem as we did in the first problem, which is that this is an equation with 2 variables, right? It's a function, but it's a function of r and h, and we don't know how to take the derivative of something with 2 variables. You will in Calc 3. So we, again, use our restriction. We have to have a restriction. If I just said make me a big can, you just make me a big can. Our restriction is that it has to hold a fixed volume. So that liter is a measure of volume. And here's where we need that. So we set up our equation for volume and we say, okay, that equals 1 liter. The volume of a cylinder is pi r squared times h. If you didn't know that, don't worry about it. I'm not going to make you memorize geometry formulas for the upcoming test or whatever, but the volume of any cylindrical type shape is just the area of the top times the height Technically, a rectangular prism is also a cylinder in mathematics. Cylinder means a lot more than the way we're using it right now. Again, don't worry about that until Calc 3. So pi r squared times h, that's the volume of our can, and that has to be 1 liter. And here's where I don't know how you would do this not using the metric system. A liter is 1,000 cubic centimeters. If you didn't know that, that's okay, you're American. Our dimensions of our can, our radius and our height, are going to be in centimeters. So that's why the metric system is cool, because we're measuring this. A liter is 1,000 cubic centimeters. So the 3-dimensional measurement for volume has something to do with the 2-dimensional measurement for length. They're related, which they should be. Think about if I gave this to you in gallons. Does anyone know how many cubic inches are in a gallon? That's a trick question. You don't know, because why would you? Because those two things are completely unrelated, because our measurement system is completely dumb and unscientific, and we should have scrapped it years ago. Anyways, so all that means for us is that we're just going to change 1 liter to 1,000 cubic centimeters so that our units are right. Our answer is going to be in centimeters, and wouldn't you know, it just works out fine because metric system. So pi r squared h, the volume has to equal 1,000 cubic centimeters, and same deal, we have to solve that equation for h to get h in terms of r to stick that back into the surface area equation. So there's always, well, not always, sometimes these involve doing like a little substitution. That's easy to do. You just divide both sides by pi r squared, right? H is 1,000 over pi r squared, and then we're going to take that and go back up to that SA, to that surface area equation, stick that in for h, so that all we have left in there are r's. We could have done it the other way and solved this for r and stuck that back in, but think about why we didn't do that. It would have just given us a more complicated expression, which is fine, but then we would have had to take the derivative of that more complicated expression, then we would have had to set that equation equal to 0 and solve it. So let's, work smart, not hard. That goes back into S, so our surface area finally, just in terms of the radius, is 2 pi r squared plus 2 pi r times 1,000 over pi r squared, because that's what the height has to be based on our radius. Right, and that's a function. That's a function of a single variable r. It cleans up. So now that we're getting into applications of derivatives, before where I said, okay, don't simplify. If all you're doing is finding me a derivative, just leave it messy. But now we actually have to do something with it. So you generally always want to clean it up before you do that, right? Before you start doing any algebra, get it as nice as you can. So stuff cancels out, a pi canceled out, and an r canceled out. So 2 times 1,000 over just r. So it's our function for surface area is 2 pi r squared plus 2,000 over r. So that's the thing we now get to optimize. All right, you can forget about the can for now. Now it's math. So this is just, again, just think about it as f of x, 2 pi x squared plus 2,000 over x. You know how to do that derivative. One thing we always want to keep in mind is that to do the derivative of something like 2,000 over r, don't use the quotient rule. That's goofy. Just write it as 2,000 times r to the negative 1. Convince yourself that that is the same thing, because that's just how exponents work. So now you can just use the power rule to do s prime. Power rule says, okay, that 2 hops out front and multiplies by the 2, so it's 4 pi r. And then the negative 1 hops out front and goes down to a negative 2. So it's 4 pi r minus 2,000 r to the negative 2. And then we have to set that equal to 0 and solve it. So what I would do is put it back like that. You use the negative exponent to make doing the derivative easier, but then it's helpful to switch it back to a over r squared to make solving this equation easier, because it's easier to see what to do. You don't have to do it my way. To me, that's just the best way to do it. So we're solving 4 pi r minus 2,000 over r squared equals 0. Algebra, so I'm going to move that to the other side, and I'm going to multiply both sides by r squared to get rid of that denominator, which gives me 4 pi r cubed equals 2,000. Remember, we're solving for r, so divide by 4 pi. So r cubed is 2,000 over 4 pi. We have to take the cube root of that still, but notice that simplifies. So that simplifies to 500 over pi, and then finally we get our answer. So you can just cube root both sides of an equation anytime you want. That's 1 to 1, so nothing bad happens. Okay, and our optimal radius for our cylindrical tin can is the cube root of 500 over pi. So that's the thing with these. You probably didn't guess that number. You really don't know until you just do the math. Why is it this? Well, we just showed why it is, because that's the maximum possible value, the minimum possible value for our surface area function. There's no maximum possible value, because you could just technically keep making the can taller and skinnier or shorter and flatter until basically the height or the radius was 0, and then you'd divide by 0 and you'd have no can left. So it just is what it turns out to be. So on the 2 quizzes that are posted, both of which are pretty hard, I think I give you the answer and I say, prove it. So here's the answer you want. Now set up an equation, do the derivative, set that equal to 0 and solve that, and then you get whatever it is you get. And you'll see in particular so the rainbow quiz that's on there, you're going to prove why rainbows always appear at a 42-degree angle. It's weird, but you can do that. That's a true fact. It's called the rainbow angle, and you can do that with just calculus 1 stuff. In fact, you're going to. It's hard. It's a very hard equation to solve. But as far as like why is it that way? Well, because math. That's your job. Show me why it's that way. So the radius of our optimal can in this context, where we have 1 liter of stuff in it, is the cube root of 500 over pi, which your calculator will tell you is about 5.42 centimeters. So that number is not very meaningful, but as it turns out, when you stick this back in and figure out what h has to be, which I'm just kind of use a calculator for because the numbers are ugly. If you just stick 5.42 in for r there, you get h is about 10.84, which, look at those 2 numbers, right? The height is twice the radius. And it turns out it's exactly twice the radius. It's just to show that is just messy, and we can take my word for it. Okay, so in an ideal situation, if you want to make a can and use the least amount of stuff possible, you're going to make the height twice as much as its radius. Or, in other words, make the height equal to the diameter of the top. And again, the liter thing didn't really matter. It wouldn't matter how big our can was. The dimensions are the dimensions. So if you had a big old can of popcorn or something, or a tiny little can of, I don't know, capers, it wouldn't matter. This would be the ideal way to make it. And if you measure a can, go measure your can of beans or whatever, this is actually pretty close. Unlike the last problem, which wasn't very realistic because boxes have to fold and stuff, this is actually pretty darn close to like the classic Campbell's soup type of can. It's not exactly what you'll see because you have to crimp it over the top and stuff, and you have to cut the sides and the tops from other sheets of metal, and then you also have to pack them. So real life is a lot more complicated than this. And it's still math, it's just a lot harder math. But basically, that's why the cans you have in your cupboard are shaped the way that they're shaped. So you can hold a certain fixed amount of volume using the least amount of material possible. And it's the same as the last problem, and life isn't always this simple, but hey, look, one thing is exactly twice the other thing. Why? I don't know. That's just how it turns out, and that's what optimization is.